And so what you probably saw was we have our CH3 plus, right? 3 plus. And so we just took the number of electrons, right? And so carbon has how many electrons? 4. Hydrogen. Yeah, 3 from those. And then what do we do because of a plus? Subtract 1, yeah. Got it. And so we have 6 electrons we have to account for. We put what in the middle? Carbon. What do we do with the surroundings? Yeah, so we make bonds to each of the hydrogens. Okay. And so what do we do then? Yeah, we have to add the formal charges, right? Yeah. So we've accounted for all 6 of our electrons. That part's done. We don't have to do any lone pairs, none of that. But we do have to deal with charges, don't we? And so our formal charge is going to end up going on our carbon in this case, because it's 1 down. And we can't actually shift it off onto those hydrogens, can we? Okay? Because they just don't have any extra electrons.
Yeah. We need to know the equation for formal charge.
Yes. All it is the number of electrons it normally would have minus the number of electrons that it has now. Yeah. So it's actually kind of easier to remember it as what its purpose is. Okay. Anybody have any questions on any of that? Did we need any more practice or anything? Are we good to go? You'll notice there is a problem in the homework that you'll do that. I didn't bother putting up the key because it was going to be very long and I didn't think you guys really needed it. If you need something to help you with that, I wouldn't recommend starting here, but Wolfram Alpha actually has most of these structures on it. Okay? Most Lewis structures, can you just put it in Wolfram Alpha and it'll pop out. Okay? Most of the AI models are not super good at it. You can check it out and try it if you want. Let me know if they do anything decent. So these are average bond lengths and bond dissociation energies for different selected types of covalent bonds, of course. You've probably seen this way more times than you would want to see it in your life because it gets shown basically every single chemistry because there's various different uses for these, right? Okay, so you've seen it in organic chemistry, you've seen it in general chemistry, and now, yay. You'll see it a little bit more in physical chemistry, and yeah, it'll be a thing. Okay, does anybody have any questions about this, other than the fact that instead of angstroms, we're in picometers, right? Okay, these would be like 0.74 angstroms and that sort of thing, if you're doing them in angstroms. Okay, it's 100 difference. All right. Which of these are stronger, by the way? Is this one stronger or that one stronger bond? The higher number means stronger or weaker?
Weaker. Well, no, because the farther away you are, the less repulsive.
Yeah. So the smaller you are for bond lengths, then the tighter it's being held, pulled together. Okay? Or another way of saying this, this larger bond dissociation energy, that's the energy to break the bond. So having larger number means stronger bond, right? Now that, in this case, this is kind of a weird, like, showing here. Because we're seeing sort of different things being shown to you, right? This right here being a nitrogen-nitrogen bond, you're probably mostly thinking of N2, which is a triple bond. Okay. Okay. So this right here is the equivalent forms, the canonical forms of ozone. When we look at this arrow, you'll remember from organic chemistry that this is not a reaction arrow, right? It's a resonance forms arrow. And so that means that these two structures together give you the actual structure for it, right? Okay. We just can't write it in Lewis structures, and it actually makes sense. Okay, So if you were to look at this, you would actually see this has a 50% contribution from each. In reality, these are like 1.5 bonds. They're actually the same length. Okay? And these two oxygens have sort of similar electron densities around them, right? That isn't true for all of these resonance structures. They are not all necessarily 50-50 contributions. What would dictate the sort of contribution you'd expect to see out of these things? What if I have a structure that has a negative charge on carbon for one of these resonance structures versus oxygen? Would you expect that to be as likely? No. And so that's a lower contribution usually. Okay? And it means, yeah, they're still the sum of, but it may only be a 20 versus a 50% contribution. So there's some negative charge on that carbon, but it's not as much as you would see on the oxygen. Okay? Okay. All right, so this right here, there's 3 forms right here. Notice they're all similar in terms of likelihood, and so this would be like a 33% contribution for each of these. Is everybody okay with this so far? Okay. Okay. In this case right here, we have 3 non-equivalent forms of thiocyanate ion. And so these conical structure B would be the one that you would come out with from the Lewis structures. Can anybody tell me why you would come out with that one? So what's that last step? What do we use to determine which of those electrons should go in? We're trying to minimize formal charges, right? Minimize formal charges next to each other. And if you're going to have a formal charge, what should you have it on? Exactly. And so, for example, here we have formal charge on the most electronegative, but we have maximized formal charges, haven't we? So it's a -2 there. This one right here has a -1 on the nitrogen, doesn't it? And so that one is the canonical one. It's the one you should come out with in a Lewis structure. It's the most representative. Okay? But it doesn't perfectly represent this molecule, does it? No. This one here, less likely, isn't it? -1 charge on the sulfur. Sulfur is less electronegative, isn't it? Okay. Everybody okay with that so far? Okay, fantastic. Again, these right here are the rules that you would go through, and that would tell you the most likely Lewis structure. These are all valid Lewis structures that contribute towards the overall structure. But this one's the most true, okay? Or the most canonical, most representative. All right. These are not in order, by the way. People get tripped up on that a lot and go like super dedicated to one. Yeah. There isn't really an order. You sort of just have to minimize all of them as much as you can. So the average bond lengths for SC and CN in these bonds, a variety of compounds, are listed here. And so this is sort of the average bond length of an SC on a bunch of different compounds. Okay. So let's sketch any reasonable canonical forms of N2O, and let's identify their relative contributions to the overall resonance hybrid. The experimental bond lengths for NN and NO bonds for N2O are going to be 113 picometers, 119 picometers, so that respectively. These are some average bond lengths that you can compare, and that will tell you what your canonical should look like, right? That will help you. Because if you're closest to one type of bond, guess which type of bond best represents that? So let's say your bond distance is closest to the double bond. What type of bond is most canonical? Double bond. Yeah, it's most representative, right? Okay.
Sorry, can you say that again?
So if you have, let's say you look at these bond lengths, right? And your bond length is closest to a double bond versus a single bond. What's going to be the one that's more representative of that bond? The double bond, right?
You're saying like from the table, like
Yes.
in the column if it says...
Yeah, so here we have experimental numbers from this compound. Okay? And here, these are average bond lengths for these types of bonds, right?
Oh.
So for example, if we look at these bond lengths, then that bond length for NN in here is much more representative of like a triple bond than it is a single bond, isn't it? Yeah. So if you're putting single bonds as being your canonical structure, no, that doesn't have as much contribution, does it? Yeah. Okay, folks. So go ahead and start trying to write those out. Everybody get the compound we're working with? N2O. You knew I was going to ask you to do it first. Come on. Ooh, I need to start doing that. I need to start splitting those parts. I think I finally figured out what's happening with my not being able to open the book properly on the computer. My TPM has been corrupted. It's really weird. And I'm having bad luck with everything. Okay, folks. And so you may notice that you essentially end up with a structure that has an N in the middle, right? And then on one side there's a single bond N, and the other side there's a single bond O, and then you have valence electrons, right? And at that point you have to deal with formal charges to figure out which one would be the most canonical, and that's the branching point for your resonance structures, isn't it? Okay? And so you have one possibility where you could take in two of the lone pairs off the nitrogen side, right? And that'd make a triple bond nitrogen, wouldn't it? Okay. And a single bond oxygen with a bunch of lone pairs. What's one of the other structures you could do? Hmm?
Both of them having a double bond.
Yeah, both having a double bond. So you contribute a bit, one lone pair from the oxygen, one from the other nitrogen, right?
And would that one be better because the NO bond was 119, which is a lot closer to the literature value as opposed to the triple bond? So would that make it more likely to have two double bonds?
Let's talk about that in just a second. Okay? It'll take a bit of nuance, and we kind of need our resonance structures first. Okay. What's the third option? So instead of taking them all from the nitrogen or evenly split, we could have taken them all from the oxygen, couldn't we? Okay, and we ended up with a triple bond and oxygen. That's probably not super likely, is it? No, that seems like a very strange structure. And in general, that gives you a lot of oxidation number, doesn't it? Okay. Okay, and so these seem like the more likely ones, right? A and B, the first two we had talked about. In fact, you guys kind of just discounted the third one completely, probably. But it is a resonance form. It's a possibility, right? If we did something interesting, like, for example, we took a metal ion and we put it up in such a way that we could attack on the nitrogen, maybe we could do some interesting chemistry, okay? Or we could put something to stabilize charge on the nitrogen. But anyways, okay, so now we're going to talk about the picometers and bond lengths, right? Okay, so we look here, and this is 113 for the NN bond. That would be between the nitrogens, right? And this would be 119 for the NO bond, right? Between the nitrogen and oxygen, okay? Okay, and so we look here, and we see that it's 119 here, right? And that's closest to this one, isn't it? Okay? And we see a 113 here. That's actually closest to this one, isn't it? Yeah. So what we're saying is these are the two major contributors, isn't it? Okay? And we're actually seeing a lot of contribution from those. Now, one of the things that might actually end up causing us a bit of an issue here is we actually end up with this form here that has these partial positive, partial negative charges right next to each other. Okay, so they can actually equal out quite easily and shift between. This obviously being the almost no contribution at all. Yeah. Okay. Did that answer your question?
Yes.
Yeah. Yeah, it's, remember that they have contribution towards it for both of these. And so for this, what we're looking at is an averaging of a double and triple bond. And that would be these two averaging out, right? And for this one over here, the oxygen, we're looking at an averaging out of the double bond here with technically the single bond. But we're seeing this is more of a contribution, isn't it? And so it's actually closer to the double bond. Yeah. Okay. This is the bond dissociation energies. There's a few different ways you can actually work through this. But a correlation is actually made. Remember that correlations we talked about when we were converting those to the electronegativity scale? Because the electronegativity scale was arbitrarily set to 4. Okay. So this right here, you can actually use your bond dissociation energies to figure out the electronegativity of a compound, i.e. how well it holds on to electrons in those bonds. And so you can actually generate a revised Pauling electronegativities list. This is actually in your book at table 311. And again, we need a correlation factor, though, whenever we do this. That is going to be this right here. So that's the difference in the bond dissociation energies. That's the average there. And then we take that value, we take the square root, and we times it by 0.102. That actually will give us the electronegativity differences between those. Pauling's decision actually causes us a lot of like weird issues because 4 has no real unitary base, right? It's not like he derived it from joules or something. He didn't. Or coulombs or anything, right? It was like 4.0. Great. Nothing to do with it. So all of these equations that actually are real things that you can measure always have to have these weird correlation factors. Because the 4.0 scale has nothing to do with anything at all. Like, yeah.
Oh, they just change it so it does.
Partially it's because, like, what would you change it to? Because a lot of these are calculated very different ways. Coulombs, joules. Like, which of the units would you choose? So instead of one group winning, no group wins. But whatever. Like, it's functional. If you've done all this calculation, then doing that one's fine. It's not an issue, right? Yeah.
What did you say BDE is?
Bond dissociation energies. Yeah. Yeah, they're this big long thing that we had just, yeah. And so this is another way we can go about measuring these electronegativities, often experimental value that you can obtain by simply breaking bonds apart and seeing how much energy it is. Okay. Okay. All right. And so this right here, you may recognize these. This is the difference in electronegativities versus your average electronegativity. And notice that out here we have covalent, and when these things form together, they form covalent bonds, right? Out here we have ionic, and this is the wedge that gives you ionic bonds, and that's the cutoffs that gives you ionic bonds. Note that in reality, there's some parts where you could argue. Okay? The lines can be blurry and blurred a little. But overall, we don't normally fall on the lines. Okay? In most bonding situations. Okay, so here we see the ionic. If you have that combination of your electronegativities, you're going to be considered an ionic bond, right? Right here we see metallic bonds. What does metallic bonding mean? Hmm?
The mobile sea of electrons.
Kind of. Kind of. It's going to be where metals are close enough that they can actually start sharing electrons. And so it's a little bit different than the sea of electrons model. It actually means it does have some bonding. It's like kind of like the covalent bonds of metals. But they aren't quite the same as covalent bonds because they still have sea of electron metals. They still are metals. They still do all the things metals do. So they're not quite covalent bonds. And this is why you see this green part right here. You have like this gradual shift over in these pseudo not ionic bonds, covalent bonding systems. But you have the metals, you have the non-metals doing it, and then you have the stuff that is starting to get electronegative enough, it's starting to have some more non-metal-ish properties, less metal-like. Okay? And that's this stuff here. All right. Again, a lot of this class is adding shade to the black and white world you had been operating in Gen Chem, right? Yeah. That's just not how the world works, right? Yeah. Yes, everything's quanta, but those quanta are pretty small. So, this right here is actually the electronegativity differences in these compounds. And again, this is the one you've probably always done before, okay? Where you had done these electronegativity differences. And so here we have the electronegativities. These are the electronegativity differences as you go up here. And what we can see is when we get to the maximum electronegativity difference, that's ionic, right? And then we go down from there, and we start transitioning into covalent, and metallic is over here, okay? So this is where everything has very low electronegativities, so they very easily lose electrons, and the electrons get shunted about, and they have a tendency to sort of detach and move around in these things. And so even your contained bonds would be very delocalized and move around a lot. Yeah. Here we have more traditional covalent bonds that you're used to. Okay? And so, for example, F2, very strong, super contained, very sigma. Okay? Is that making some sense? Okay. And that's sort of the stereotypical model you'd always thought about. Okay? And then we get a little bit further down here, and we're still covalent bonds, but we're drifting apart from what you thought about as a covalent bond as super contained. Electrons don't move from between those at all. Okay? Okay. And so like hydrogen, you'll notice hydrogen does some kind of weird stuff, and boron does some weird stuff, right? Yeah. If you're in organic chemistry right now, we're doing borates, right? Boron. Yeah. Boranes.
Like a fluorine bond, why is that length of the bond so short? Like whatever
That's because
atom
it's so
has the
far
same
over.
two atoms,
Yeah,
so short.
it's the electronegativities.
And okay, but
So-
like they both have the same electronegativity.
Yeah.
Fluorine.
So what's happening is you have those electrons, and both of the fluorines are so damn electronegative that they hold on to those electrons super tight. So if you were to like, you and someone somewhat equal strength to you were to grab a single object and you're trying to pull it towards you, you're both going to start pulling each other towards you, right? And you're going to get real close when you're trying to do this. Does that make sense? If you were weaker, you're not going to pull each other as close when you pull, right? Because your body weight will matter more. Does that make sense? Okay. Yeah, that's what you're seeing there. That's actually causing this, that super high electronegativity covalent. Yeah. And that actually is that same relationship. You'll see a pattern that follows this exactly. Okay? It's not a linear it's not a relationship that you can just like, this is this number very easily. You have to do a calculation, right? But okay, so the polar covalent bonding in the HF molecule right here, and what we can see here is this has an uneven distribution of electrons, right? And what would we normally call that? Polar covalent, right? But in reality, what that always was is we had a percent covalent and we had a percent ionic, right? And polar covalent are situations where we aren't in the high percents covalent, right? We're lower percentage covalent than normal. Like we're a 70% covalent, 30% ionic sort of situation. Okay? And that's where we start going into the polar covalent bonds. And so how you would actually calculate that is this is percent ionic character. You take 0.33 times your electronegativities for your two atoms that are involved in the bond, the difference between those. Notice this is a square function, and it's a square function because all of these functions, these force functions, are always square functions. Okay? It's actually kind of interesting because you can actually approximate values really easily by just taking square roots of the results. Yeah. And you can get a very nice trend that you could then graph. So if you ever wanted to graph like the force versus the bond, you just take the square root and you'll get the force bond matching. Yeah. You'll get the nice linear relationship. And that has to do again with the fact that it's a hockey stick, right? Yeah. They're not normally linear relationships. Yeah. And so we're correcting those. Okay, so right here, this is the bottom term. It's plus 1 plus 0.33, and then it's just that same relationship again. Okay? Electronegativity A minus B squared. Does it actually matter which one you do first, by the way? If you actually put it in your calculator properly? No. If you put A first, B first, you just flip a sign. If you take the square of anything, so that's why you're like seeing me like, hey, I don't care. Times 100%. Let's try this problem real quick. Can you guys even read that? Okay. Using the revised Pauling electronegativities from the table and apply equation 4.7. Calculate the percent ionic character for each of the following molecules. We'll just do HF real quick. And so you'd look up HF. You'd use this formula right here, percent ionic character. That's what we're trying to do. And so we get the 4 scale. It's actually a 3.98 technically scale. Because
The electronegativity, so like the XA minus XB thing, is that for, so that's like,
fluorine and hydrogen.
sorry.
So all you're doing is just looking up F, which should be 4 technically, but it's not actually because when they set the scale, it wasn't.
But it's,
Yeah.
it's like if it's blown into itself.
You'd have 3.98 minus 3.98,
Okay.
and that'd be 0 term then.
Yeah.
And by the way, this is why you have to do this terminology like this, 1 minus. If you had like just over something, you'd have divide by zeros. Yeah. So they defined it very carefully when they did this. Yeah, so we look up the fluorine, of course. We look up the hydrogen, which is 2.20. Probably the same numbers you've seen before. So we take 4 minus 2.20, or 2.00 minus 4, I don't care. And then we square it. We do that same number times 0.33. We keep that number aside. On the top, we put that number. On the bottom, we take 1 minus that number, right? Okay. Okay. And what do we get? You got it. 51.1%. What does that tell you about that bond? Yeah, it's 49% covalent. 51% ionic, isn't it? Okay, it's mostly ionic. We're actually further towards ionic than we are covalent, right? Yeah. And that's why that is such a drastically charged molecule. Yeah. Okay, so this right here is your two-centered, two-electron model here. And what we can see again is we have two centers, which are nuclei, right? In each of these cases. And they're joined together by a single bond, which has two electrons in it. Okay? And what we can see is this would be, for example, hydrogen, hydrogen, and they're equally split, and the electrons spend time around both, about equal. And where does the majority of the time for those electrons spent? Around the nuclei, and a bit in the middle, right? Yeah. Those are the main spots, though. Mostly like near the nuclei in the middle-ish. Okay. This right here is then hydrogen fluoride, and where's the majority of the time spent on those electrons? Yeah, the fluorine, right? By quite a bit. Yeah. The fluorine gets the majority of the time of those electrons. Yeah. It's that 51% ionic character, right? Okay, this right here is lithium fluoride, and what do you notice about this? Where's the majority of time spent for those electrons? Yeah, the fluorine. In fact, it's so much so that look at the density in the middle between. All these other ones, it shows white, which means that we've stopped being able to increase. And so it's maximum contour. It actually doesn't spend a lot of time in between, does it? Yeah. So this one is very, very mostly ionic. Okay? This one is a very ionic situation. All right. This right here is actually an electron density profile. We have the contour diagram here, and this one here is the just a like a cartography map of that. Okay? And what we can see here is we actually get some interesting behaviors for this. This here is what you would normally write this. It's diborane. You may recognize that from organic chemistry. My organic chemistry people probably do, because I just made them do that for a while. And, my people that didn't have me for organic chemistry, do you recognize that okay? No? Oh, that's sad.
What did you say that was?
Diborane.
Diborane?
Yeah, borane is BH3. And this is the diborane. And so this actually happens for kind of an interesting reason here. So you can actually see that the electrons here are not actually shared around the borane or the borons completely. They actually have some external conditions. See these peaks here? Yeah. Where the electron density is actually being held. Okay? And we can actually see that in the core, this mapping here too. See how it's really high around the boron, and it's high around the hydrogens, but also has some pretty high areas that are sort of in between, right? Yeah. Okay, so this again is the plane of the atom here. And again, we can actually see the plane of the atom actually has a much more, this is this one up above. So these ones are in one plane right here. And then these hydrogens are above and below. And that's what you're actually seeing right here. Okay? And that's one of the reasons why we had that kind of interesting shaping to it. So this is the boron, boron, hydrogen, 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 hydrogen in that plane. Right there. And then this one right here is the hydrogens here. Can you see that other one behind there? Kinda. Okay. Anybody have any questions about that? Okay. Yeah, so this is actually a pretty interesting case where the hydrogens actually act to pull these together, and it has to do with the electronegativities. because boron's not that different electronegativity wise from hydrogen, is it? Okay. I'm going to just barely start on the next one, I guess.